Astrobiologists are hiding an uncomfortable truth about alien life. Scientists quietly suspect we might be completely alone, and here's why that scares them. Buckle up, because today we're diving into the cosmic odds why aliens might be way rarer than Hollywood wants you to think. What does it take for life to exist in the universe? Maybe it's a high-maintenance, nitpicky kind of thing, something that only happens when everything lines up just right. A process where every single molecule has to be in perfect order. Or maybe life gets going pretty easily. Just mix together a few random organic molecules and boom, life shows up. Both of these ideas fit with what we know so far about life, which honestly is just us. All life on Earth is related, distant cousins tracing back to a single microbial ancestor called LUCA, the last universal common ancestor. So despite all the wild diversity we see today, we're all just offshoots of that one lucky break. Maybe there were other attempts that fizzled out, but right now we've got zero proof of that. Here's the thing. The fact that life made it at least once doesn't really tell us much because, well, duh. It had to happen at least once or else we wouldn't be here thinking about it. Life might be crazy rare in the universe, and if that's the case, it's no surprise we ended up in one of the few places where it worked out. Because for living things like us, there just isn't another option. That means just existing, us or the whole tree of life, doesn't help us answer the biggest question of all. How often does life get started? If we ever found a second totally separate tree of life, that would prove life got going at least twice. And here's the kicker. That second start would have nothing to do with us. Whether it happened or not doesn't affect our existence. A discovery like that would blow the whole debate wide open. It'd probably be the biggest scientific breakthrough ever, proving we're not the only game in town. Sure, over the years, there have been tons of claims about life out there. Oceans on the moon, artificial clouds on Mars, Martian meteorites with fossils, biosignatures on Venus, and of course UFO sightings and alien encounters. But not one of these past claims has cleared the bar for solid scientific proof, repeatable observations with a clear-cut explanation. The whole Martian canals thing is a fascinating case. We've covered it in detail before on this channel, that shows how easily human bias can mess with our objective take on alien life data. Now, just because we haven't found proof yet doesn't mean it's not out there. Life could be super rare, super common, or anywhere in between. So once again, the fact that we exist doesn't give us any real clues. Actually, trying to use this as evidence creates a circular argument. Because obviously the fact that we can even ask these questions depends on life succeeding at least once. A much stronger clue is how fast life showed up on Earth. Crazy fast in just a few 100 million years. In one of our earlier papers and videos, I explained how this quick start still comes with some big question marks. But overall, it suggests that if we could hit rewind and let Earth's history play out again, we'd bet 9-1 that life would pop up quickly once more. If you think 9-1 odds are a safe bet, then this one data point seems to settle the debate, right? Rewind Earth's clock and life comes back. Therefore, life should be everywhere in the universe. Well, hold up. It's that second step where we've got to be real careful. Because remember, I'm talking about replaying Earth's exact conditions. Same orbit, same mass, same starting atmosphere, even the same rock sitting in the same spots. But if I move just one pebble or shift one volcano or nudge a continent, does that mess everything up? Like the butterfly effect, maybe even a tiny change could totally alter life's fate, maybe for the way worse. This is where the famous rare earth hypothesis comes in. First proposed by Professors Peter Ward and Robert Brownlee, it's now a major and hotly debated idea in astrobiology. As the name suggests, it argues that Earth's conditions are freakishly rare, perfectly balanced for life. If that's true, then the fact that life started fast here doesn't really matter because planets like ours are so rare that life almost never gets a shot. Or another take, one that matches the original idea better, is that Earth-like conditions are especially crucial for intelligent life. Sure, there might be microbes on Mars, but if you want civilizations, you gotta have something almost identical to Earth. So what exactly makes Earth so special, according to Ward and Brownlee? Some reasons are pretty obvious, like size and mass. Too small, and the planet's gravity is too weak to hold on to a thick atmosphere. Too big, and the stronger gravity could trigger runaway growth, turning it into a gas giant. The next obvious factor is being the right distance from your star, so liquid water can exist on the surface. When the book came out in 2000, we honestly didn't know much about either of those factors. But of course, in the years since, we've discovered tons of exoplanets, and now we finally have some answers. For example, we know rocky planets are common around normal stars. However, we still don't know how common rocky planets are in Earth-like orbits around Sun-like stars. You can check out our previous video to learn why. The rare Earth idea goes way beyond just mass and orbit, though. To understand better, I'll point out 4 other key factors that rare Earth supporters often mention. First, a habitable planet needs a magnetic field to protect it from dangerous radiation. This has become really important recently as we think about sending astronauts to the Moon or Mars for long periods. Earth's magnetic field shields us from harmful radiation by deflecting charged particles. Since the Moon and Mars don't have strong global magnetic fields, this radiation could give astronauts cancer or radiation sickness. Of course, one solution is for astronauts to just stay underground, either in caves or by piling dirt on top of their base. Actually, Earth kind of does this for us automatically because our atmosphere is much thicker. In fact, famous astrobiologist Jim Casting has argued that Earth's thick atmosphere might be enough to protect us even without a magnetic field. This idea is supported by the fact that life survived just fine during Earth's many magnetic pole reversals. So maybe the magnetic field isn't absolutely necessary after all. Second, plate tectonics might be necessary for life and could be rare. The main idea here is that the movement of Earth's plates helps recycle important nutrients and chemicals. When ocean plates slide under continents, we basically recycle materials that were locked in rocks, fossils, and oil. The heat breaks these down and they eventually come back up through volcanoes. Scientists think this recycling helps keep Earth supplied with the ingredients life needs. But again, some disagree, saying that Earth-sized planets would naturally develop plate tectonics and that you could still have geological activity without it. Third, we need to consider our moon. Our moon is unusually large compared to the planet it orbits. 5 factors. And yes, I'm skipping the geology stuff for this example. Notice how each one builds on the one before it. Take FH, for instance. It's not about all planets in the habitable zone, just the rocky ones. This is what we call conditional probability, and it's super important to keep in mind. This whole chain of multiplying conditional probabilities looks a lot like the famous Drake equation that estimates how many civilizations might be out there in our galaxy. Actually, the connection goes deeper because the Drake equation specifically includes a term for what fraction of planets are Earth-like. That means we could swap out that single Drake term with these last four factors from our rare Earth equation, just like this. What this shows is that the rare Earth hypothesis basically takes that one Earth's term from the Drake equation and breaks it down into a bunch of more specific requirements for true Earth twins. At first glance, this seems like an improvement, right? We're making the Drake equation more precise with better math. But is it really better? One clear advantage is how flexible this math approach is. Maybe you don't think a big moon is necessary for life, but you believe you need a sun-like star instead. No problem. Just swap out that factor in the equation and you've still got four rare factors left. We'll call this version Scenario A. On the other hand, maybe you think Earth needs way more special conditions than just these four factors. Maybe you'd add requirements about the solar system's location in the galaxy, or the planet's original atmosphere, or the ratio of land to ocean, and so on. You might end up with something like 80 different must-have conditions for true habitability. Let's call that Scenario B. So what's the difference between Scenario A's 4 factors and Scenario B's 80? To keep it simple, let's say each factor has a 50% chance of being met. For example, the first factor, the probability of a planet being rocky, is 50%, which happens to be about right. In Scenario A with 4 rare Earth factors, the final probability of getting an Earth-like planet is 1/2 multiplied by itself 4 times. We can write that as 1/2 to the 4th power. Crunch those numbers and you get 1/16, or about 6.25%. That's uncommon but not crazy rare. Now let's run Scenario B. With 80 factors, we're looking at 1/2 to the 80th power. That's 1 in a trillion trillion, or 10 to the -24. That number's so absurdly small that even if you checked every star in the observable universe, you wouldn't find another Earth. Of course, picking 50% for each factor was completely random. The real purpose of this exercise was to show how crucial the number of factors is. We tend to obsess over debating whether individual probabilities should be 1% or 10%. But honestly, the bigger question is how many factors belong in the equation to begin with. Here's the problem. We don't actually know how many factors we need. These factors are supposed to represent all the conditions required for a planet to support life. If we had a solid, universal theory of how life begins, we could calculate the necessary parameters from scratch. But we don't. We're basically clueless about life's origins. Without that knowledge, some try to use Earth as our one data point, reverse engineering what life needs by studying our own planet. But drawing conclusions from a single example is incredibly shaky ground. Many critics argue this is exactly what Ward and Brownlee are doing. While they make reasonable cases for their chosen factors, we've seen there's plenty of disagreement about them too. More importantly, we can't actually test any of these claims until we find life elsewhere in the universe. And this is where my main concern kicks in. The whole approach of reverse engineering Earth as the gold standard for life is fundamentally human-centered. It quietly assumes our path was the only possible path for intelligent life, that our particular history represents the sole route to consciousness. Let's be honest, we all fall into this trap in daily life. We build our worldviews based on our personal experiences, often ignoring the vastly different realities others live through. To truly understand life, both our individual lives and biology as a whole, we need a broader perspective. I know this might sound like I'm getting too philosophical, and sometimes I do indulge that, But let me show you a concrete mathematical consequence of this thinking when it comes to life's origins. I'll admit, the argument that humanity resulted from a string of incredibly unlikely events holds water. First you need X, then Y, then Z. And sure, as we pile on more requirements, the odds do get ridiculously small. But here's the key. That might not be the only recipe for intelligence. There could be totally different paths to civilization we haven't even imagined. Take a world without its own magnetic field, but what if it's a moon orbiting a gas giant that provides that protection instead? Completely different setup, but it could still cook up intelligent life eventually. Here's the problem with equations like Drake or rare earth. They assume there's only one narrow path forward. Each term builds on the last, funneling everything towards something that looks just like us. But searching for intelligent life isn't just hunting for our cosmic twins, it's way bigger than that. Maybe we should add parallel paths to these equations. Say a planet never forms a big moon. That doesn't automatically mean game over for intelligence. It might just open up a completely different path we can't even picture yet. Suddenly, we're not just multiplying probabilities in a straight line. We're adding up multiple possible paths to intelligence. Could be a few, could be one, could be countless. We simply don't know. This is why I don't buy into the rare earth hypothesis. Now you might think that means I believe Earth-like planets are everywhere. If I reject X, I must believe the opposite of X, right? That's the false either-or thinking the media loves to push these days. But science doesn't work that way. It's perfectly fine to say I don't know yet when we lack evidence, which we absolutely do right now. I'm not a skeptic or a true believer. I'm just waiting to see what the data says. As I've said before, this approach matters. If you claim to believe in rare earth without solid evidence, you're setting yourself up for a painful reckoning when, not if, real data comes in. And let's be honest, nothing's harder than admitting we were wrong, especially publicly. Too often we twist new information to fit our old beliefs, grabbing at anything that supports what we already thought. Because being wrong feels awful and being right feels great. You don't need me to tell you this, we all see it happening every day. But here's the thing, when it comes to life in the universe, we're flying completely blind. No data means no need to take sides. You don't have to plant your flag on questions we can't answer yet. The answers will come someday, even if it takes generations. And when they do, we'd better check our human-centered biases at the door. No preconceptions, no wishful thinking. Just clear eyes and open minds, ready to hear what the universe actually has to say. Until next time, stay thoughtful and stay curious.